Okay, so we need to know what an angle is, first of all. And an angle is just two rays with the same endpoint, called the vertex. Here's some angles. So remember back at the beginning of the course we talked about quantities. And we said quantities are measurable attributes of objects, right? Quantity is a measurable attribute of an object. So an angle is an example of an object. It's just a thing in the world, okay? That is the two rays, same endpoint, called the vertex. Okay, so what does it mean for two angles to have the same measure? What does it mean for two angles? So now we're talking about a quantity. So we want to measure, quote unquote, measure an angle. Well, that's talking about now, thinking about a quantity. So the quantity of angle measured. What does it mean for two angles to have the same measure? Any ideas? Yeah. Okay, so the openness of the angle is the same. Yeah, Dan?
Would that be like a straight 180 degrees?
No, we're going to talk about any angle. So that's one particular angle, a straight angle, but I'm talking about any angle. What would it mean for any angle to have the same measure as another angle?
Same on both sides.
What's that?
The same on both sides.
Same on both sides. Same what? Okay, what's degrees? So degrees is a unit. So we're talking about what does it mean for two angles to have the same. So degrees didn't come first. Angles come first, and then we have to devise a way to measure them.
The same distance around the circle.
Same distance around the circle. Okay, cool. These are all good ideas. Do you have another idea?
Same fraction of a circle.
Same fraction of a circle. Okay. Yeah. So really, we have to. If we're going to talk about the measure of an angle, we really, before we answer that previous question, we really have to say, what are we assigning a value to? What is it we're assigning a value to when we're measuring an angle? And so all your ideas were good. And Jacob said the openness of the rays. And this is the attribute of the angle that we're measuring. Okay? This is the quantity that we want to measure is openness of the rays. Okay, which of these angles has the least openness? A, B, or C? And then the greatest? What has the greatest openness? B. Okay. So what about distance between the rays? That's an often what people think. Distance between the rays. So what about the distance between the rays? So what's the, what's this distance? So think about this distance right here. Okay, the distance between the rays. And then I could look at this distance right here. Does distance between the rays correspond to amount of openness? So I'm showing you, oh, that was a bad example. That's the wrong example. So try again. This is what I meant. So that distance and this distance. That's better. Does distance between the rays correspond to amount of openness? No, this is a less of a distance here than this is here. But this one's more open, right? You said B was the most open. Okay? So it's not about distance between the rays, because as soon as you move away from the vertex, the distance is changing, always. So distance between the rays doesn't work, but openness works. You think of a door, okay? How open is the door? So the more open the door is, the greater the angle, measure the angle. The less open that the angle is, the lower the value of the measure of the angle. Yeah, Michael?
So rays are infinite, right?
Right.
As far as length. Okay, so if you were to take it at somehow get the exact same measurement, like of both angles, you know, I say like the exact same distance out.
Right.
Would it then somewhat properly?
Yes, somewhat, right? So if you took the same distance out from the vertex on different angles, then you have some, that'd be better. That'd be better. But we're going to do even better than that, okay? Not straight line distance. We'll do even better than straight line distance. Okay, so then so here's the whole question. How do we actually assign a value to the openness of an angle? Okay, what's the basis for measuring angles? So how are we going to actually assign a number to how open the angle is? No, not a straight line. Not a straight line. Okay, so let's talk about that. So you have to for this next exercise, you have to kind of erase everything you've learned about angles in the past. We're going to design a pizza cutter, okay, from scratch. And so what we're saying is we're talking about the openness. So you see that this very cool pizza cutter with the scissors has an angle there, right? So there's some amount of openness here. That's not supposed to be going up the scissors, right? Like this, okay. All right. Okay, so that pizza cutter is defining some amount of openness, right? And this one over here is too. So you see, like right there, that's defining some amount of openness that will give you a slice of pizza, right? So we want it, without knowing anything in the past about angles, we want to design a V-shaped pizza cutter, whether it's the one on the right or the left, whatever, so that it will cut the pizza into 9 equally sized wedges. Okay, and we want to create a blueprint for the cutter. So, but you don't have any protractor, you don't know anything about degrees, you don't know any formulas, okay? So what you have is just like common household stuff. Desk supplies, pencil, ruler, tape, scissors, string, okay? And you want to design a blueprint that will design a pizza cutter that will give us exactly a pizza with 9 equally sized pizza pieces like these. Okay, so I'm going to take attendance, you can work together. Again, you don't have a protractor, you don't know anything about degrees. Just these things. And we're going to figure out how to design a blueprint for the pizza cutter to get 9 equal pieces of this shape. Is the task clear? So actually this is in your book. It's number 2, Module 8, Investigation. Module 7, Investigation 1, number 2. What page is that? So, can you do it without using the diameter?
Yeah.
What do you want to do?
You can take a string and put it on the outline of the pizza.
All right, so take a string and wrap it around the pizza?
Yeah.
So we're going to do better than the first class? Maybe a little better.
Better in tests.
There you go. Okay?
And then you can straighten that string out.
All right, so he's going to go exactly the circumference. Is that possible to go exactly the circumference? Wrap it around exactly? Sure. And we're gonna straighten it out, and then what?
Measure the total length.
Measure the total length.
And then divide that number by 9.
So he's gonna measure the total length and divide it by 9. So let's see how I do here. How do I do? Is that 9? 1, 2, 3, 4, 5, 6. I do it twice every semester. I'm getting better at it. Okay. All right, then what?
And then once you have it marked, you can wrap it back around, and then it'll show you where to cut.
Okay, so now we've got 9 equal parts of the circumference. Wrap back around. So like there. 2, 3, 5. Okay, something like that. Okay, let's see you do better in that amount of time. All right, and so then what are you going to do? So you got these, so these parts of the circumference are all equal and 1/9 of the circumference. Yep. And then we're going to? Yep, so we can then, assuming that we can find the center of the circle, we can draw in the center. Thank you. Okay, so how many people came up with that? Or something like that? About half. Okay, so this is a way we can do it without knowing anything about degrees or any angle. So we can take a string and measure around the circumference. and then straighten out the string, get break it into nine equal segments, wrap it back around, and that defines where we would cut, or how we would how much openness we would have for our piece that would give us 9 pieces. So the point of this exercise is to say that angle measure has everything to do with a circle, the circumference of a circle. You have to, it's about the circumference of a circle that forms the basis of angle measure. So let's talk about that, or summarize that. So the angle of measure is based upon, so there's kind of so we could say the percent or fraction of a full circular rotation. What percent of going all the way around? That will give us an amount of openness, right? An amount of openness. What fraction or percent of going all the way around? And then more similar to the pizza example, so like how much arc length relative to the whole circumference? What fraction of the circumference does the angle cut off? What fraction of the circumference does the angle cut off? So measuring an angle this way, what is the measure of the angle for one piece? Measuring this way, what's the measure of the angle of one piece in our blueprint? How would we put a number on that then? What number would that be? Any ideas? We're saying percent or fraction of a full rotation or length of arc relative to circumference. One hole? One hole? That was our angle? So our pizza, what's that? He wants 1/9. What do you think? 1/9, yeah. So our angle that we ended up designing on that pizza cutter was a 1/9 angle. Or whatever percent that is, 1/9. What is that? 11% or something, 11.1%. Okay, so here's another angle. So now, when we come to an angle and we want to think of it this way, we need to put that vertex in a circle, right? And now we can talk about what amount of openness is that. Measuring angles the way we're talking about. What amount of openness is that? What is it, Andrew?
Looks to be about a quarter.
1/4, 1/4, right? So this would be a 1/4 angle, or a 25% angle. Because it's everything to do with a percent or fraction of the circle or fraction of arc length around the circle. So here's one. Take the vertex, put it on the center of a circle. What amount of openness is this angle? What is it? A third? Nah, it's 2/3. I meant this one. So just from what I showed you, there was actually two different, there's the 1/3, you were looking at the 1/3 openness, but this other one is the 2/3 openness, right? So the one that's further than halfway around, further than halfway, that amount of openness is 2/3. Okay? What about this?
Which angle?
6.
Not 5/6, 1/6. Yes, right. It could have been either one. It could have been 5/6 or it could have been 1/6. So I'm showing this one now. So that amount of openness, that angle is a 1/6 angle, or about a 17% angle. Okay, so now this gives us a basis for actually talking about degrees. What are degrees? What does an angle of 1 degree represent? So is this a lot of openness or a little bit of openness? It's like a sliver of openness, right? So something like that. This is like 1 degree. So zoom in on that a little bit. So how can you describe this is actually, if you turn the page, what is it?
So 1
million? No, you know what it is. 1. Okay, so it has to do with 1/360th, but just to say 1/3. Okay, so yeah, so our angle, right. Thinking of the previous screen, we call this a 1/360th angle. But so we want to be a little more specific now. So 1 degree represents what? Okay, so 1/360th is what? What are we talking about here? Yeah.
Is that the arc length?
Okay, the arc length relative to the circumference. Right. So here's kind of a full explanation. An angle with measure of 1 degree, its vertex is placed at the center of a circle, has rays that's subtended arc length, that's 1/360th of the circumference. So this word subtend, we'll think of it, so the way we're going to think of subtend is, it means like cut off a piece, okay? So these rays cut off a piece of the circumference. And so it's that fraction of the circle that we're interested in that gives us the measure of the angle. So subtend means like cut out a piece. The rays cut out an arc from the whole circumference. So if it's an angle measure of 1 degree, then the rays cut out 1/360th of the circumference. Okay, so just practice this with those other two examples. So at the top of that next page, you should see, I think it's 10 degrees and 47 degrees, is that right? So kind of practice this language. What 10 degrees means what? 47 degree angle means what? Go. Okay, so that was intending to invoke about 20 conversations, but it invoked none. So get a partner and explain it verbally. You can write it out, that's fine, but verbally explain what 10 degrees is, or an angle with a measure of 10 degrees, and what's an angle with a measure of 47 degrees. Go, so talk to the person next to you. Okay, Sean, tell me what 10 degrees means.
It would be an angle with a measure of 10 degrees that subtends an arc length of 1/36th of the circumference of the circle.
Okay, so if an angle has a measure of 10 degrees, its rays subtend how much of the circle?
1/36th.
1/36th, right? If it has a measure of 10 degrees. And if it has a measure of 47 degrees? What do you think? Nathan?
It has rays that subtend 47 over 360
Of the circumference, right, exactly. So a 47 degree angle has rays would subtend or cut off 47 360ths of the circumference of the circle. Okay, so this idea of percent of a circle or fraction of the circumference gives us a way to talk about what are degrees, right? So what are they? So does anyone know where 360 came from? It's kind of so ingrained that we just think that circles naturally are broken up into 360 pieces, but that was a man-made invention. That was a man. So circles don't come with inherently something about 360, right? That was a man-made invention. So why did they pick 360?
They kept drawing lines across it.
Okay, so yes, this 360 has a lot of nice factors, right? 1, 2, 3, 4, 5, 6. What? 8? I think no. 9, 10, 12, right? So it breaks up really nicely, 360. And so there's another reason too. Is that? No, there's no connection between 360 and Why did they pick 360?
Skateboarding thing. You go on
Skateboarding, right. Babylonians and their skateboarding.
Just due to the size of the number where it would have more degrees in it, is that part of it?
Okay, not what I was getting at. Andrew?
Everything has to do with Archimedes and triangles.
Triangles? Anybody know where 360? It's close to what number? 360 is close to? 365. So it was there. Had kind of guessed that that was the length. It's 360 days in a year. So they knew it was close to that. So that was another reason why they picked 360, because it was. They were relating it to how many days in a year. So I don't know if they were still thinking that the sun went around the Earth at those times, but whether the Earth went around the sun or the sun went around the Earth, it's still they were thinking that was 360 days. Yeah.
So it seems like the Earth's orbit slightly. Well, yeah, that's why it's 365 instead of 360, because it's slightly elliptical.
I don't know why it exactly is 365. I don't know what the reason is, but in their science, they were coming up with an estimate that it was about 360, and then 360 had all those nice divisors, like lots of nice ways to break it up. So that's where 360 came from. Okay, so let's talk about a different way to measure angles. Here's where I need my circles. So first of all, do these show up as gray? Do they show up now? Enough? Can you see them? You just need to see them. That's faintly is fine. Okay, so I've got, trust me, I've got 3 circles here. Just to believe me. And I'm going to do this. Did you see what I did there? I'll do it again. Ready? You see what appeared? We'll zoom in a little bit. Zoom in. That's better. So what did I just represent by putting that pink bar on there? The radius of which circle? Smallest. Okay, so that radius length is 1. Now watch. I'm going to take that radius length and I'm going to take it off of its normal position and I'm going to move it up and wrap it on its circle like that. That was the coolest thing you saw all day. Okay, I'm going to do it again. So there's our radius 1 is normal spot, right? The distance from the center out to the edge of the circle. And I'm going to pull it off and wrap it on the circle, maintaining its length of 1 radius length. Okay, oh shoot. What am I doing now? What does that represent? The blue one. Radius of the middle circle, which equals to? Same thing. Pull it off its spot, wrap it on its circle. One more time. What does the red bar represent? Which is 6. It represents the radius of the biggest circle, 6. Wrap it onto the circle. So now I've got a question for you. So I want you to brainstorm. What are some mathematical things that are, in the context of mathematics, what is the same, different about these 3 arcs, and what is the same about those 3 arcs? So as many things as you can think of. What's different about those 3 arcs mathematically? There you're gonna have a little powwow. Okay. So what's different about those 3 arcs, and what's the same about those 3 arcs? As many things as you can brainstorm. Go. So mathematical, not color. Okay, let's hear what you came up with. How about different? Cameron, did you come up with something that's different about those three arcs? Arc length, what do you think? Their length. Are they different?
Yep.
Sure. The length of the first one is 1. Length of the second one is 4. And then 6. Certainly different. How? So using the units of the axes as a measuring stick. One is 1 arc length, and the first arc length is length 1. The second is length 4, and the third arc is length 6. Anything else that's different that you came up with? Okay. That's kind of the main one, right? Anyone come up with something else?
The circumference of each of them be different?
The what's that?
The front circle, so.
Okay. How about the same? So what's something that's the same? Dan is dying to tell me.
Well, the degrees / radians / fractions are the same.
Okay, how about just one thing, and we don't know what radians is, and so when you say the degrees is the same, so let's talk foundationally, right? So what are you saying there by that?
So when I say the degrees are the same, I'm saying that when you, I don't know the exact degree on this, but the subtend of each of these
Okay.
will be exactly the same.
Okay, so right. So if we had an angle, you're saying that those would all, the angle would cut off all three of these.
Yes.
The same angle. Okay. What else is the same? Other ideas? Yeah, Jacqueline.
They take up the same percentage of these circles.
They're the same fraction of their circle. Their circumference, the same fraction of their circle. That sound familiar? Okay, so, yeah, right. So they have the same fraction of their circumference, or it sure looks like it, right? This isn't, proof. It sure looks like they're taking up the same fraction of their circle. And so if that's the case, then by definition of our definition of angle, that they're defining the same angle measure. So let's just kind of, maybe we can check that a little closer here. So where we're gonna start the angle on the positive x-axis. So look at the positive x-axis. So this is going to be our starting side of the angle here, okay? And so this is the initial side. Since it's at one end of the arc, it's the initial side. And the terminology we're going to use is the 3 o'clock position. Why? Because it's pointing right at 3 o'clock if the circle was a clock. Okay, the initial side is in 3 o'clock position. And what we're going to do is we're going to starting there, we're going to sweep an angle, maybe. Oh, why? What happened? Something happened here. There we go. I don't know why that happened. Okay, so we're going to sweep an angle counterclockwise. And does that, so do they all terminate at along the same lines? We're asking, do those arcs all terminate at the same line so that they all subtend the same angle? Yeah, okay, so what do? We're going to sweep counterclockwise, that's what we did, from the 3 o'clock position to the terminal side up here. So this is called terminal side of the angle. And it sure looks like that angle now subtends the same amount of arc length relative to the circumference, right? So, is there anything else that's the same? So, anybody else come up with something? There's something else that's the same about all three of these. Different way of thinking about this. Anyone come up with another thing that's the same about all of them? Okay, what if instead of measuring, was that it? Jenna, is that an idea?
I don't know if it's what you're looking for.
Okay.
But you can multiply any of these values by 2 pi to get the circumference of the circle.
Okay, but we don't know. So what's that? So it's kind of, if we're building on what we've talked about before, we don't know what 2 pi is. Okay, Sean.
Like all the way around the outside, I guess it would be.
But no, let me interrupt you. We're talking about what's the same about these three arc lengths. What's the same about these three arc lengths? Arcs. Okay, it has to do with measuring their length. So if we measure their length with the units of the x-axis scale, then they're different. 1, 4, and 6. But what if we measured them in terms of radius length of their circle? So what if I measured this in terms of the radius of its circle? What length would it be in radius length of its circle? 1. And then I took the blue one and I measured it in radius lengths of its circle. Still 1, right? And what about this? The red one is also 1 radius. So depending on how you measure those lengths, it could be the same or different. If you measure it in radius lengths of its own circle, then they're the same length. They're all 1 radius length. Okay, and they're all subtended by this particular angle that I'm showing. Okay, so since they're all subtended by this angle, and the length is 1 radius length, this amount of openness we call, it's not what I wanted. This amount of openness we call 1 radian. So where does the number 1 come from? So 1 radian is the amount of openness. Okay? The number 1 comes from how many radius lengths are cut off by the rays. So there's radius lengths and there's radians. They have the same value, but radius lengths is measuring arc length and radians is measuring openness of the angle. Does that make sense? So this is this distance here is 1 radius length. And this distance here is 1 radius length. So is this 1 radius length. And they all define an angle measure of 1 radian because that angle is cutting off 1 radius length of arc length. Doesn't make sense. Okay, so let me show you 2 radius lengths of arc length. Or something very close. So you can just look at the inner 2 circles, the purple and the blue one. So now I'm showing 2 radius lengths wrapped on the circle. What's the corresponding amount of openness of the angle? 2 radians. Okay, this seems so elementary, but when things get harder, there's angles, arc lengths, and there's some context, and everything's flying around. This very principle is super important that you don't lose sight of it. That the number of radius lengths cut off by the angle is defining how many radians of openness that angle is. It's the same number. It's the same number. Okay, finally we'll do 3. So now I'm going to have an angle that cuts off 3 radius lengths. the angle that cuts off 3 radius lengths. So you're just looking at the. Okay, so this angle here, almost halfway around, shy of halfway around. The length of that blue arc or that purple arc is 3 radius lengths. Therefore, this angle has what amount of openness? 3 radians. So where do radians of openness come from? They come from how many radius lengths do the rays of the angle cut off? It's the same number. But radians is openness, radius lengths is arc length. Okay, so now for this scenario that I've drawn, that you're looking at right here, for the scenario you're looking at, I want you to build a table. Okay, and so the table is going to be, so we have the purple arc, blue arc, and red arc. Okay? And some more place to write here. So do over here. So purple, blue, and red. And for each of those, so we need symbols first. Okay, we need symbols. The first symbol we need is for measuring openness. Measuring openness, that's theta. So theta is angle measure, or the measure of openness. Okay? S is arc length. So this would be like in axis units. Okay? In the units of the axes. And then R stands for radius length in axis units. Okay, so our symbol theta, that's angle measure. That's the symbol that stands for the angle measure. S is arc length, measured in the axes units. Okay, and then R is radius length, also in axis units. So for each of P, B, and R, I want you to build a table here. And I want you to write down what theta is, what R is, and what S is for each of those 3 arcs. Is the task clear? So what is theta? Theta is angle measure. R is the radius length measured in this unit right here, 1, 2, 3, 4, 5, 6, 7, 8. And S is the actual length of the arc measured in axis units, 1, 2, 3, 4, 5, 6, 7, 8, like that. So for the situation I'm showing, the static situation that I'm displaying, you're going to fill in that table. If you can fill in that table, then you're on track with what we're talking about. And then make observations about the numbers, kind of generalize. We want to generalize what's happening in this table, okay? So go. You work together, compare results. You're filling in this table for each of the 3 arcs. What's theta, what's R, what's S? Got done? Reading emails, that's honest.
Square root of 2 over 2 root of 2.
What is it? Is we'll always subtend the same angle measure. Okay, what is our radius of the purple circle? Okay, and therefore, what is the length of that arc? If it's okay, is it 1 or 3? So this is the length of the radius, and this is like how many radii we're going. So therefore, 3. What is the radius of the blue circle? 4. So if each radius is 4, and we've got 3 radius lengths, 12. What's the radius of the red circle? 6. Each radius is 6, and we're going 3 radius lengths. So what's the general idea here? That the length of the arc is what? Yeah. Radius times theta. Okay, and we know, so theta is representing openness, but it really helps to be able to kind of switch back and forth in your mind, because in this formula, it would be really nice to think about this as number of radius lengths, right? And you can, because it's the same number. You take the number of radius lengths times the length of one radius, that's going to give you the total arc length. It should make perfect sense, right? So you have to have that kind of versatility to think of theta, since it's the same number, as, in this formula, you think of it as number of radius lengths subtended by the angle. So it's like, okay, I'm doing this many radius lengths. Each radius is this long, so I'm just going to multiply to get the total length of the arc. Does that make sense? And the table tells the story, right? That if we have 3 radius lengths, each one is 6 long, it's going to be a total of 18 units long, the arc. Right? The arc will be 18 units long. And that's just what this is saying here. S equals R theta. Okay. We got one more thing to do. Any questions on what radians are about? We'll review it again Thursday. But the number of radians, the openness of the angle, comes from the number of radius lengths that are subtended by the angle. Okay, so let's zoom in here. So here's 3. That's so big. Let's make that a little smaller. Okay, so there's 3, and then here's 4. So let's mark off where 4 is. So then the question is, how many radius lengths, or how many radians of openness, will get us exactly halfway around the circle? So there's 3 up here, and there's 4 down here. So I want the number of radius lengths to get me exactly halfway around, because that's just a helpful, useful thing. You want to think about half a circle. So, what would you guess? 3.5? 3.3. He said 3.3. Maybe a little less than that, right? 3.2, 3.1, something like that. Some of you know already. But you know, but you didn't know. Okay? So let's try 3.1. So here's 3.1. Let's zoom in. Here's 3.1, and here's 3.2. So let's try halfway between those. Here's halfway between, 3.15. Too much or not enough? A little bit too far. So how about 3.14? There's 3.14. Halfway, not halfway, or a little bit past halfway? Not quite. So now most of you know what's going on. So how should I make it closer, Dan? How should I improve on 3.14? 159. Here's 3.14159. I'll zoom in. So you've been working with pi all your life, but did you know that pi is what? The number of radius lengths to get halfway around the circle. If you take the radius length and put it lay it on the circle, it takes pi of those to get exactly halfway around. That's the point. And so then the measure of a straight angle is how many radians? The measure of a straight angle? How many radians is that? If it's 3.1, if it's pi radius lengths around the circumference to get halfway around the circumference, then the openness of a straight angle is pi radians. Okay, web work will be up soon, and then it'll be due Thursday.